Let's begin. The last speaker of today's conference is Meesue Yoo from Chunguk University, and she's going to talk about combinatorial description for the Hall-Littlewood expansion of unicellular LLT and chromatic quasisymmetric polynomials. Let's welcome her.
Thanks a lot for the introduction, and thanks a lot for inviting me to this conference. Before I start, I need to ask you understanding. I had the COVID like 2 weeks ago. I think I'm not contagious anymore, but I still suffer from some coughing. So I would like to ask your understanding for my coughing during the talk. So I'm going to talk about the combinatorial description for the Hall-Littlewood expansion of unicellular LLT and chromatic quasisymmetric functions. And this is joint work with Seung-Jin Lee of Seoul National University. So in this picture, this is a summary of what I'm going to talk. Given a dict path, there are two symmetric functions indexed by this dict path. One is this chromatic quasisymmetric function. The other one is unicellular LLT polynomials. And I'm going to consider the Hall-Littlewood expansion of these two polynomials. One is the original Hall-Littlewood, and the other one is this Twitter modified transformed Hall-Littlewood. And the coefficients are related. I'm going to compute these coefficients reading out from this dict path picture. So before I start, I'm going to introduce the natural unit interval order and chromatic quasisymmetric functions. So the natural unit interval order, say we have a sequence of positive integers which are weakly increasing, and the ith component is larger than or equal to I for each I. So I'm considering the sequence of length n minus 1. But if you consider a sequence of length n, then the last entry is going to be n. So it's a redundant information, but that's also okay to consider the length of n sequence. So given this sequence m, the natural unit interval order is a poset on the elements from 1 to n. And the order relation is defined by I less than j if I is less than n and j is between mi plus 1 and n, including the boundary values. So given this sequence m, we can consider the dict path having the column length mi for ith column. So the first column has length 3, 3, and third one 4, and so on. And the last one is length 10, which is n. In that case, the order relation of the natural unit interval order is encoded in the partition shape, which is above the dict path. And then what we can also consider is the incomparability graph of the poset. This is a graph having the vertex set as the elements of the poset. And then between two vertices, there is an edge if these two elements are not comparable in the poset P. So in terms of this graph, the edge information is encoded in the cells between the dict path and the main diagonal. So the cells here means there are edges in the incomparability graph, and the cells above the dict path means there is a comparable relation in the poset. Now, I said that I'm going to consider the chromatic quasisymmetric functions. So let me define the chromatic quasisymmetric functions for any simple graph. I'm going to consider a coloring, which is just a function assigning positive integer values to the vertices. And the coloring is called proper if two vertices are connected by an edge, then the coloring value should be different. So now I'm going to compute the chromatic quasisymmetric function over all possible proper colorings as a summation of these Q-powered monomials, where Q power ascent statistic comes from the number of edges, which satisfies this condition that the vertex labeling and the coloring values have the consistent comparability. So if I is less than j in the vertex labeling and the coloring values also satisfy the same inequality condition, then we count that as an ascent. So that defines the q power, and you add up this q to the ascent times the monomial coming from the proper coloring, and then that defines the chromatic quasisymmetric function for the given graph. But I'm going to consider this chromatic quasisymmetric function for the incomparability of the natural unit interval order. In that case, rather than considering this graph, we can consider this thick path picture. So this graph corresponds to this thick path, and the edge relation is encoded in the cells between the thick path and the main diagonal. And the q power, so I'm going to label the diagonal cells from northeast to southwest, starting from 1, 2, 3, 4, and 5. So these are the function values, proper coloring function values. And the proper condition means that if there is a cell in the intersection of this column and row, then these two values should be different. So keeping that condition, I fill the cells, the diagonal cells, with positive integers. And then the ascent statistic, I count the cells if the column label is larger than the row label. So this one, since 3 is larger than 2, I put q there. And also here, 2 is larger than 1, so I put q. And 3 is larger than 1, so I put q. So for this monomial, x1, x2 squared, x3 squared, I have q to the q cubed coefficient. So we consider all possible proper colorings over this thick path picture and add them up, then you get this chromatic quasisymmetric function corresponding to this graph. And the reason why I consider only this incomparability coming from the natural unit interval order process is because of this e-positivity conjecture of Schurz and Wax. They made this conjecture in 2016 and saying that if the graph is in comparability graph of a natural unit interval order, then the chromatic quasisymmetric function is going to be E positive. In other words, if you expand this chromatic quasisymmetric function in terms of the elementary symmetric function, then the coefficient is going to be Q positive. And this is a Q deformation of the famous Stanley-Stamburich conjecture, E-positivity conjecture. So if you solve this conjecture, then you automatically solve the Stanley-Stamburich conjecture. So in that sense, this is an important problem, and that's why we consider this incomparability graph of the natural unit interval order. But I'm not going to consider the E expansion of the chromatic quasisymmetric function, but I'm going to consider the Hall-Littlewood expansion of XG instead. But this explains why we only consider those graphs. So that's it for the chromatic quasisymmetric function part. And let me define the other symmetric function, which is unicellular LLT polynomials. But let me just define the LLT polynomials in general first. So LLT polynomials are the symmetric functions introduced by Lascaux, Leclerc, Thiebaud in 1996. And they came up in the process of studying the Fock space representation of UQSLN head space. And in the process of studying this space, it's natural to consider the ribbon tableau. So they originally defined this polynomial in terms of the ribbon tableau, and they call this polynomial ribbon polynomial. But later, Bylund and Heyman came up with an alternative definition, which are defined over a K-tuple of skew diagrams. So we're going to use this definition instead. Say we're given a K-tuple of skew diagrams, and over these skew diagrams, we're going to consider a semi-standard Young tableau. So SSYT of this tuple means product of or K-tuple of skew semi-standard Young tableau. And given a tableau in this set, we're going to count the inversion statistic. So inversion statistic comes from these two cases. One is when two cells are on the same diagonal and the function value or the filling value of U is larger than V, or these two boxes are in the consecutive diagonals and the filling value in U is larger than the filling value of V. So we count all those inversion pairs, and inv statistic is the number of inversions in this T. And then the LLT polynomial is defined by the summation of Q to the inv times the monomial coming from this T. You sum up all these monomials, the Q-weighted monomial, then you get this LLT polynomial. And Bylund and Heyman proved that this definition and the original definition is just Q weight difference. So it's equivalent to consider this LLT polynomial defined in this way to consider the original definition. But what we are going to consider is when these Q shapes are only single cells, and those are called unicellular LLT polynomials. Oh, but before we consider the unicellular LLT polynomials, let me say something about LLT polynomials. Why are they important? So LLT polynomials are symmetric. And when Q equals 1, those are nothing but the product of skew Schur functions. So this is this could be considered as a Q deformation of product of skew Schur functions. And Gronowski and Heyman proved that they are Schur positive. So it's an important question to consider to get the combinatorial formula for the Schur coefficients of LLT polynomials. But here, as we can see, LLT polynomial is a Q deformation of product of skew Schur functions. Now, Schur expansion of one skew Schur function, the coefficient is Layte-Richardson coefficient, and that's an important statistic. But now we have to consider K-tuple of Schur functions, and above that we have Q weights. So computing this Schur coefficient is going to be a very hard problem. But in any case, the reason why we consider this question as an important question is because Haglund, Heyman, and Rohr found the positive expansion of McDonald polynomials H mu Twitter in terms of LLT polynomials. So if you know how to compute the Schur coefficients of LLT polynomials, then they will give automatically the information of the QT-Casca polynomials, which are the Schur coefficients of McDonald polynomials. So in this sense, that's also an important question. But also, I'm not going to consider the Schur expansion of LLT polynomials, but I'm going to consider the Hall-Littlewood expansion of LLT polynomials. But I'm just saying that LLTs are important. So I'm going to consider unicellular LLT polynomials, which is the case when the skew shapes are all single cells. And in that case, we can transfer this picture, the skew shape diagram, to the disk path diagram on the right-hand side. So the way we draw this disk path is as follows. If two boxes are possible in position, then you put this cell under the disk path. For example, 1 and 2, if the filling value in this box 1 is larger than 2, then they make an inv. So we put this box here. And 2 and 3 are also in the possible inv position. So we put box here. But 2 and 4, these are not in possible inv position. So this cell in column 2 and row 4 is not under the disk path, but above the disk path. So in that way, this picture can fix one disk path. So we compute the unicellular LLT polynomial in this disk path diagram. And then inf statistic also can be computed over this disk path diagram. So we consider all the possible fillings over this diagonal without any conditions. And then for the cells under the disk path above the diagonal, the main diagonal, we compare the column label and the row label. And if the column label is larger than the row label, then we put Q there. So in that way, we compute the inf statistic over the stick path. And then you sum up Q to the inf times the monomial coming from the filling over the diagonal, and some summation of all the possible monomials, the Q-weighted monomials will give the unicellular LLT polynomial. Now we've seen two symmetric polynomials. One is the chromatic quasisymmetric function, and the other one is unicellular LLT polynomial. Now I computed both polynomials over a disk path, and I used the ascent statistic to define this chromatic quasisymmetric function, but to make two polynomials similar, I'll use this inf instead of ascent. But the way of computing this inf statistic is just the same as the inf statistic for the unicellular LLT polynomials. So these are very similar, but the only discrepancy is that we have this proper condition for the chromatic quasisymmetric function, whereas we didn't have any condition for the unicellular LLT polynomials. In other words, we could just put any words for the main diagonal, but here we have proper condition, means if two vertices are connected by an edge, then the cell should have different values. But other than that, they look very similar. So there must be some connection between these two symmetric functions. And the proper, the explicit relation was disclosed by Carson and Mallet in 2018 upon the proof of shuffle conjecture. And they are related by this plate disk substitution. So you put Q-1 times X plate disk substitution for the LLT polynomials and divide by Q-1 to the N. Then you get the chromatic quasisymmetric function indexed by the same disk path. So I'm going to use this relation to relate the Hall-Littlewood expansion of these two polynomials. So I said I'm going to consider the Hall-Littlewood expansions of these two polynomials. So let me introduce what the Hall-Littlewood polynomials are. So this Hall-Littlewood polynomial was came up in Anna Poon's talk yesterday. And this one is actually not the original definition, how we define the Hall-Littlewood. But I'm going to use this form for the sake of my convenience. So this is the original Hall-Littlewood symmetric function, and which can be defined as a summation of Kaska-Fuchs polynomial divided by this pro-gamma symbol times modified Schur function. This is a Schur function, statistically substitute x times 1 minus q. So let's just define the Hall-Littlewood polynomial in this way. And when q equals 0, then you get the Schur function. And when q equals 1, they become the monomial symmetric functions. And when the indexing partition is just one column, then the Hall-Littlewood becomes elementary symmetric function of size n, which is Schur function indexed by one column shape. So I'm just saying that the Hall-Littlewood polynomials are kind of Q analog of all the known symmetric function bases. And then I'm going to also consider the modified transformed Hall-Littlewood polynomial by H mu Twitter. And H mu Twitter is just a summation of K lambda mu Twitter times Schur function. Here, K lambda mu Twitter is just some transformation of the Kaska-Fuchs polynomial, which can be defined by a charge statistic. And this one is defined by co-charge statistics. So it's known to be a positive Q polynomial. And if you just compare the definition here, we get rid of this denominator. And then instead of this modified Schur function, you just use the Schur function, then you have H mu. And by transforming this K lambda mu one more time, you get the H mu Twitter. And we get some reminiscence of this Carson-Melick relation here, because we are getting rid of x1 minus q platistic substitution here. So they are going to be related by this Carson-Melick relation. Now I'm ready to explain what I'm going to say. So I'm going to consider the Hall-Littlewood expansion of LLT and chromatic quasisymmetric functions. Say you have this H mu Twitter expansion of unicellular LLT polynomials. And the coefficients look like this. You have some Q power and Q minus 1 power, and then Q positive polynomial here. And if you use the Carson-Melick relation to this expansion, then you get the chromatic quasisymmetric function, which is expanded in terms of the original Hall-Littlewood polynomial. And the coefficient looks like this. And the interesting thing is that you have the same polynomial d gamma mu, but Q replaced by Q inverse. So the good thing is that if you are able to compute this polynomial, the unicellular LLT polynomial, the H mu Twitter expansion of unicellular LLT, then you automatically get the coefficient of original Hall-Littlewood expansion of chromatic quasisymmetric function. So that's what I'm going to explain. Here is the theorem. The original Hall-Littlewood expansion of chromatic quasisymmetric function looks like this. And this coefficient is going to be root polynomial. And then using the same root polynomial with Q replaced by Q inverse, you get the H mu Twitter expansion of unicellular LLT polynomials. And this is a theorem. And I'm going to explain how you get this root polynomial. So you need to know a linked root placement. Let me explain what a linked root placement is. Say this is the partition shape, which is above the dict path. And then I'm going to place a rook, a linked rook. Now, basically, rooks attack the cells in the same row or column. So you're supposed to place at most one rook in each column or row. But then our rook is going to be linked. So I say I place the rook here, and then the rook emanates away. And when it hits the main diagonal, it bounces up. Then you can place any rook in this column. Say I place the second rook here. And then if I want to place more linked rooks, then you do the same. It emanates away. And then if it hits the main diagonal, it bounces up. And then you can place any rooks in this column, but there is only one cell. So you place a rook here. So this is a linked rook. And a linked rook on these cells, 1, 4, 4, 6, and 6, 9, corresponds to a subset of 1, 4, 6, 9, which consists of the entries occur in the coordinates of the rooks. I mean the cells in the rook. So a linked rook of length 3 corresponds to a subset of elements 4. Then we can define a linked rook placement of type mu, means we place non-attacking linked rooks of length mu I minus 1. For example, when mu equals 4, 3, and 2, then I place non-attacking linked rook of length 3, 2, and 1. So I placed length 3 rook before, and then we avoid this column and this row. So I start from here, and then I place this linked rook of length 2. And then I also avoid these columns and these rows. And there is only one spot here to place the third rook. So this is a linked rook placement of type 4, 3, and 2. And that corresponds to a set partition of 1 through 9 with elements 4, 3, and 2. And the reason why we consider this linked rook placements is because the chromatic quasisymmetric functions are computed over the set partitions, and that's why this is going to be the base set of the computation. Now I'm going to define how we do the rook cancellation. The rooks will cancel some cells. The zeroth rule is going to be that rooks cancel the cells containing the rook itself. So if a cell contains a rook, then that cell is cancelled. And then the first rule is that every rook cancels the cells above. And this rule has the highest priority. There are going to be some exceptional rules, but in any case, if a column contains a rook, then the cells above that rook is going to be cancelled, are going to be cancelled. And then the second rule says that singletons cancel the cells to the left and above. So if there is a singleton, means a rook itself, which is not linked, then it cancels the cells in the co-hook to the left and above and itself. Now we have linked rooks, so we need to have linked rook cancellation as well. Say we have a linked rook, and the left and bottommost rook cancels the singleton cancellation, means it cancels the cells above and to the left. And from that on, the rooks connected to this one, to the right and above, they will cancel the entire row containing that rook. So it just cancels the cells in the entire row, of course, within the partition shape, and also the cells above. So that's the rule, the main rule, but there are some the uncancellation rules or exceptional rules. Say these are two rooks contained in different linked rooks, and I need to define a concept of length of a rook. So for a rook contained in a linked rook, the length of a rook is going to be the number of rooks which are connected to the left and bottom. So I only consider the rooks linked to the left and below, not above, even if there are more rooks connected to the right and above. For the sake of the length, I'm only considering the rooks below and to the left, or itself. Say say we have these two linked rooks, and these are part of the linked rooks. And this rook, since it's a part of a linked rook, it's supposed to cancel all the cells in this row. But this cell here, which is in the bounced column of this rook, it emanates a ray, and then it bounces up here. So this cell is contained in this column. And this cell is going to be uncancelled if the length of R1 is larger than or equal to length of R2 minus 1. And the second exceptional case is this one. Again, from the linked row cancellation, the cells in this row are supposed to be cancelled by R2, but the cell in this bounced column from R1 is going to be uncancelled if the length of R1 is larger than or equal to length of R2. I have some examples. So here, this cell here is supposed to be cancelled by R22, but this one is in this bounced column of R12. And since the length of R12 is 2 and the length of R22 is 2, which satisfies the exceptional condition, so this cell is going to be uncancelled. And the same thing happens for this one. But now for this cell, R24 is going to be cancelled this cell, and the length of R12 is 2 and R24 is 4. So the length of R12 is less than the length of R24 minus 1. So this is not uncancelled. So it does not satisfy the condition for the uncancellation. So it just cancelled. And here is another, the second exceptional case example. Now R22 is supposed to cancel this cell here. But now this is the cell contained in the bounced column of R12. And since the length of R12 is 2 and the length of R22 is 2, they are same. So this is not cancelled. But this one is supposed cancelled by R13, and it's in the bounced column of R22. But the length of R22 is 2 and the length of R13 is 3, which is larger. So it's not in the case of the uncancellation. So it's just cancelled. So we follow this cancellation rule. And then we define the root polynomial as follows. Given a linked root placement of type mu, you follow this cancellation rule and cancel all the cells and count the uncancelled cells. And that's going to give the UNC of P. And you add up this Q to the UNC of P over all the possible linked root placements of type mu. Then they will define the root polynomial R lambda mu of type mu. And they will give the coefficient of this chromatic quasisymmetric function expanded in terms of the Hall-Littlewood expansions. Here's an example. So we have gamma equals 2, 2, 4, 4, 5, and we want to compute the coefficient of P32, means we consider the root placement of length 2 and 1 singleton. And we had some Q power multiplied in front, but in this case, the Q power is just 0. So the polynomial coming from the root placement is going to give the coefficient X gamma coefficient, P32 coefficient of X gamma. So there are 4 non-attacking linked root placements of type 3, 2. So this one, there is only one uncancelled cell, which gives Q. And in this case, everything is cancelled. So the weight is 1. And there is only one cell which is not cancelled. So that will give Q. And this one, there are 2 cells which are not cancelled. So this one is following the uncancellation rule, even though it's in this row, because it's in this column, which is bounced column of this row. It's not cancelled. So the weight is Q squared. You add them up, then you get this Q squared plus 2Q plus 1, which was the P32 coefficient of X gamma. So at least in this example, this is true. But in general, the theorem is true. Now I'm briefly explain how we prove this theorem. So there is this theorem by Abreu and Negro, which determines the chromatic quasisymmetric function. So if the function satisfies these 3 conditions, then that's your chromatic quasisymmetric function. So the first one is the modular law or the linear relation. And the second one is the multiplicativity of the graphs. If your graph is union of 2 graphs, then the function should be product of 2 functions. And the third one is about the complete graph, the value of the complete graph case. For the complete graph case, the function value should be this one. So we prove the theorem by showing that our polynomial, our expansion, including this root polynomial, satisfies these three conditions. The first one was the modular law or the linear relation. So we need to show that our coefficient, this one, satisfies the linear relation, means the terms in the left-hand side equal to the terms on the right-hand side. This is nothing but just a tedious comparing of the terms, but our exceptional rules or uncancellation rules really do the final touch, means that makes the terms match on the left-hand side, on the right-hand side. But since it's just comparing the terms, I'm not going to say all the details. And the second one was about the multiplicativity. Say we have gamma, the dict-path gamma, and then gamma tilde is an extension of the gamma by adding this complete graph part. Then in terms of the chromatic quasisymmetric function, it's going to be the chromatic quasisymmetric function indexed by this gamma times the chromatic quasisymmetric function corresponding to this complete graph, which is this one. Then in theory, the result should be the chromatic quasisymmetric function indexed by this larger dict-path gamma twiddle. And the result of this product is equivalent to this recurrence relation of the root polynomial. And the result can be expressed in this way, and all the terms can be explained in terms of the extension of the root placement over this gamma picture to the larger picture, and then the cancellation rules of the root cancellation. So every term matches, or every term can be explained in terms of the cancellation or root placement. But I'm not going to explain all the details. But I'm saying that everything can be explained in terms of the root polynomial, root placements. And the third one was about the complete graph case. The value for the complete graph case should be this one, but it's easy to compute. So by showing that the three conditions are satisfied, we can see that our expansion is really the chromatic quasisymmetric function of the dict-path. So let me just show you the theorem one more time. By using this root polynomial, root cancellation, and root placements, we get the Hall-Littlewood expansion of unicellular LLT polynomials. And then the same polynomial gives the h-mu twiddle expansion of unicellular LLT polynomials, but Q replaced by Q inverse. So that's the main theorem. Now I'm going to finish my talk with some remark. The thing is, the Schur expansion of the chromatic quasisymmetric function was already known by Schreshan and Max. And the Schur expansion can be computed over the p-tableau. So we already know how to expand chromatic quasisymmetric function in terms of the Schur functions. And the Schur function can be also expanded in terms of the Hall-Littlewood polynomials, and the connecting coefficients are well known, Kaskar-Brooks polynomials. And we know how to compute this polynomial using the charge statistic. So combining these two identities, we actually know how to expand the chromatic quasisymmetric functions in terms of the Hall-Littlewood polynomials. Now, I use the root placements and root cancellation to get the Hall-Littlewood coefficients of the chromatic quasisymmetric functions. And this one, the combination of these two identities, compute the coefficient over the set of pair of p-tableau and semi-standard Young tableau. But the result is the same. In that case, there should be some connection between this linked root placement and root polynomial and the set of p tableau and semi-standard Young tableau, set of pairs of p tableau and semi-standard Young tableau, and the q weights, the inversion statistic coming from the p tableau and charge statistic. And not only that, there should be some bijection between these two sets, there should be some connection between the root polynomial and this statistics coming from this pair, but the bijection itself is not completely known yet. So with this final comment, let me finish the talk, and thanks a lot for listening.
Any question to the speaker or comments?
I guess I have a question. Really nice talk, really interesting stuff.
Thanks.
So there are geometrical interpretations for both unicellular LLT and these Shereshian walks functions coming from equivariant cohomology. So the Shereshian walks thing was proven by Bronson and Shao, and later Geeta K, and then more recently for, I guess, the LLT case, this was a result of Summers and Precup, as well as Mitsuya Sato. So is there a geometric interpretation of your results? Because I mean, the Hall-Littlewoods, they have this interpretation in terms of Tanasaki quotients or Springer fibers.
I don't know. So for the moment, I don't know, but I think it's an interesting question to consider. Seung-Jin, do you think it's possible to consider?
So the any geometric interpretation?
Yeah.
Yeah, just because
that's a very good question. That would be lovely to have, because you might want to like type C version of the cohomology of the Hessenberg variety. I mean, if you have a geometric interpretation, you might be able to generalize to other types.
Well, and somehow for the LLTs, there are these like A-B varieties where they're two very difficult names for me to pronounce, Eisenberg, Buchstaber, or something like this, but they're somehow twins to the Hessenberg varieties. And they kind of play a corresponding role there. And I mean, I ask about this because the H twiddles, I mean, those are the cohomology of actual Springer fibers, right?
Right.
So. But it's a little confusing.
H tilde, there is a 1 minus Q factor that I just
yeah, there's a 1 minus Q factor, and I think you had some negative exponents in there, but I'm not sure if they're somehow canceled out by your root polynomial. So.
Yeah, there are no negative Q powers, but you still have Q minus 1 to the something.
Okay. Yeah, sorry, I guess I missed that.
There is also a question in the chat. Let me see.
E expansion. I actually don't think so, because we'll have to expand the Hall-Littlewood in terms of the elementary symmetric functions. Then they will produce some coefficients. So I don't think there's a direct connection between, like, if you know the HR expansion, you don't get the expansion not like automatically. That's what I think, right?
Actually, there is some connection. Actually, I mean, first of all, the E coefficients should be written as a linear combination of these, You can, I mean, you can expand, modify Hall-Littlewood in terms of, so the practice of E is a product of one column modified maximum Hall-Littlewood. So once you know that expansion, then you can, I mean, if you compute it, you get some alternate summation of these. And if you, for some cases, I think one can show that there you can actually write in some positive way. So yeah, I mean, but that requires another combinatorics, but for hook shape, I think that's possible. When the mu is hook shape, I think what I said can be done. But in general, there's no, I don't have a possible rule.
So you mean the indexing shape of the Hall-Littlewood is a hook?
Yeah. For example, for one easy example is En, coefficient En. So there's a loop, the number, the E coefficient is N times, what was it? The number of loop placement in N by N. So, but the no loops are in the partition. So this loop placement, the number of N by the N loops, placement of the N loops in N by N board, so that there's no loop in the loop placement. That can be written as a D in terms of inclusion principle.
Okay.
If you, yeah, that's what you get for En. You can describe what I just said in terms of alternate summation of these. Is there some coefficient in front?
Maybe a sort of an easier, more naive question. Sorry to take two. If I send Q to 1, at least for the unicellular LLTs, I'm getting the regular representation of Sn, like P1 to the n. Is there an easy way for me to see this in terms of linked replacements?
Well, if Q equals 1, this is just the monomial expansion of the chromatic quasisymmetric functions.
Or, well, for the unicellular LLTs, though, it would be, because yeah, you no longer have the properness condition. So I think it's P1 to the n, but like from your models.
Yeah, but in that case, some terms are going to be gone because of this Q minus 1 factor. So nothing interesting happens, I think, when Q equals 1.
Well, or I mean, is it somehow a very obvious formula though? Because like
exactly.
Probably the only term that survives is E1 to the n.
Right.
Oh, thank you. Thanks. Okay, fair.
I have one question.
Yeah.
Can you go back to the main theorem?
Main theorem, yes.
I might have missed, but is there a known Shor or elementary expansion for the Hall-Littlewood P that might help to understand the Shor positivity or maybe E coefficients for X?
No, P's are not sure positive.
Yeah. But if there's a formula that we can try to prove the Shor positivity of X.
Jim, do you know?
Well, that might be hard.
Okay.
Because the natural basis to expand the P's in is this plathistic Shor.
Okay.
But one variant of this idea I think you could do is to work with the LLT formula. And you can expand this H mu twiddle in terms of Shors. On the other hand, you've got the Alexanderson Sulzgruber formula for the expansion into E's, which is also the same general form. You got positive powers of Q and Q minus 1. You can expand the E lambdas into Shors, compare those. That might tell you something, I don't know.
Thank you.
Any other question? If there are no more questions, let's thanks to the speaker again.
Thank you.